In this video, we're going to take a look at periodic trends. So here you can see our learning goals, which are to describe the various trends on the periodic table, to be able to explain the trends using the concepts of effective nuclear charge and shielding, and then also to be able to explain and write ionization equations for various elements. So essentially all trends is they're repeating regular patterns that you can observe in the periodic table. And the simplest example you can think of is probably the atomic numbers and the masses. Atomic numbers increase as you go from left to right, and same thing with mass. As you go from left to right, the atomic number increases, and also when you go down a group, those numbers increase. Let me just show you what I mean by that in the periodic table over here. So if we go here, here's your atomic number on top here. When you go from the left side to the right side, well, the atomic number goes up. Same thing for this period here, from left side to right side, atomic numbers going up 3, 4, 5, 6, 7, 8, 9, 10. And then also the going down a group. So for example, from hydrogen to francium, the atomic number goes up, but also the mass goes up. So we have a mass of 1.01, 6.94, 22.99, and it all goes all the way down to 223 over here. So mass goes up as you go down a group, and then mass goes up also as you go from left to right across a group. So left to right really means from this side over here, starting where lithium is, going all the way to this side over here where the neon is, and down from top to bottom means from, for example, hydrogen all the way down to francium. That's going top to bottom. And so you can observe patterns going from one side to the other or from top to bottom on your periodic table. And it's more than just those numbers there where the patterns exist. There's actually a variety of areas. The main periodic trends or patterns that we're going to see are the atomic radius, ionic radius, ionization energy, electron affinity, electronegativity, reactivity patterns in terms of metals, and then reactivity patterns for nonmetals. And you can see all the different patterns over here summarized in this figure. And we'll be able to explain what they are in a bit, but the idea with these arrows is that, for example, this would be smaller and it gets larger as you go towards the arrowhead. So, for example, ionization energy increases from left to right. So you have low here and higher here. Low here, higher, 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 higher for ionization energy. Same thing for electronegativity, increases from left to right. Now, if we look at the same color arrow here, ionization energy over here, we can see it increases from bottom to top. So the smaller ionization energy is at the bottom, and as you go up, the elements have higher ionization energy until you get to the very top over here, for example. So the electronegativity, same idea, increases from bottom to top. And other trends go in different directions. So atomic radius, you'll notice that increases from right to left. So you have a smaller radius on the right side and larger on the left side. So in other words, you get smaller as you go from left to right. So the larger part of the trend is where the arrowhead is. So when you summarize all the trends, you can summarize them using these arrows here so you can remember what direction the trends go in. We're going to be able to do that as we go forward in this lesson. So we have to explain why these trends exist. And so there's two main factors that explain periodic trends. And what we're going to do is we're going to take a look at each trend individually. We're going to state what the trend is. For example, this gets bigger from left to right, but we'll explain why that trend exists by using the concepts of effective nuclear charge, which is abbreviated ZEFF, effective nuclear charge, and then also shielding, repulsion, and distance. So the effective nuclear charge is the measure of the attractive force between the nucleus and the outer electrons, or the valence electrons. So how strongly the nucleus can pull in the electrons, and especially those outer electrons. And generally, the effective nuclear charge is going to increase from left to right across a period. So if I go to my periodic table over here, lithium, beryllium, boron, carbon, there's a higher electronegative effective nuclear charge as you go from lithium to neon. And the reason the effective nuclear charge increases from lithium to beryllium to boron to carbon, so on and so forth, is because if you look carefully, there's more protons as you go from left to right. So towards the right, you have more protons. Lithium only has 3 protons, and beryllium has 4. And then boron has 5. So there's more protons as you go from left to right. So since there's more protons, they can pull or hold on to those valence electrons they have a stronger hold on those valence electrons compared to something that has fewer protons. So that's why the effective nuclear charge increases from left to right. So that being said, for example, the valence electrons of fluorine will experience a greater pull towards the nucleus than the valence electrons of nitrogen, which only has 7 protons, whereas fluorine has 9 protons, so 2 more positive charges to really pull them in. Now, another factor that's involved in these trends is the shielding, repulsion, and distance of the outer electrons from the nucleus. So the shielding effect can best be represented using this figure over here. So here are the outer electrons, and here's the nucleus. You'll notice that the nucleus pulls the electrons in. Now, as you have more electron shells, you'll notice that the outer electrons are being pushed away by the inner electrons. And that's called shielding. It's like you're preventing the nucleus from really getting the full force of its pull on the outer electrons because that repulsion is further pushing them away. So essentially, the more shells you have between the nucleus and the outer electrons, the more shielding that's happening. So even though you might have more protons, for example, in the nucleus, at some point, if you get more and more shells, you might be trying to pull more, but because you're farther and farther away from the nucleus and there's more shells in between, you're being repelled away even more. So that's another factor as well that sort of relates to the same thing, is that the farther away you are from the nucleus, the weaker the pull is going to be. When there's more shells in between and you're farther away, that force isn't as strong anymore because you're so far away from the nucleus. So just to show you some examples of what effective nuclear charge does and what the shielding, repulsion, and distance does to one of the patterns. You might notice it here. So let's look at these atoms going from lithium to fluorine, from left to right on the periodic table. What you'll notice is, let's get our laser pointer here. Something's happening to the size of the atoms as you go from left to right, or the radius of the atom, I should say. Radius of the atom here. So when you go from left to right, you'll notice that we're getting smaller and smaller and smaller and smaller. And so if you think about it, it's because of the effective nuclear charge. Look at the effective nuclear charge from lithium to fluorine. Effective nuclear charge increases towards fluorine. And that's because fluorine has more protons, for example, than lithium. And also they have the same number of shells. So more protons, and the outer shell is on shell number 2 because they're in period 2 here. So really, this is going to have a stronger pull on the outer electrons and hold the electrons closer to the nucleus, which is why this atom over here would be smaller than the atom of lithium, for example. And that pattern sort of repeats in the next period as well, in all periods. But basically, going from sodium to chlorine, sodium is the largest one and chlorine is the smallest one because chlorine has just more protons than sodium, which results in a greater effective nuclear charge and therefore holding the electrons closer to the nucleus, and that's why it's smaller overall. But then something interesting happens. Students might say, well, okay, so, if chlorine is smaller than sodium because chlorine has more protons to pull in the electrons, why isn't chlorine smaller than fluorine? Because chlorine has more protons, so shouldn't it be smaller? Well, that's where the other effects come into play: shielding, repulsion, and distance. Remember, as you go into another period, this is period 3 here from your periodic table, there's more shells. So there's more shells kind of in between the outer electrons and the nucleus. There's another shell over here, basically repelling the electrons that are on the outside as well. So that weakens that effective nuclear force, even though there's more electrons here, because there's more shells in between the nucleus and the outer electrons. It weakens the effective nuclear force, and now we have the repelling happening as well. So that's why this chlorine would be larger than this fluorine. So essentially, usually when you're looking at trends that are kind of in a period, within a period from left to right, you can look mostly at the effective nuclear charge. But when you're looking at trends going sort of top to bottom, you're looking not so much at effective nuclear charge, but more so the shielding, repulsion, and distance. Because really, what's changing from top to bottom is the number of shells. Whereas in a period, in a row, you're not changing the number of shells. You're just changing the number of protons without changing the shell number. So their number of proton can have an effect. So all the trends that we're going to study that we listed over here, for example, they can be explained using the concepts of effective nuclear charge, shielding, and repulsion and distance as well. So again, effective nuclear charge explains trends going across a period. So generally, the effective nuclear charge is going to increase from left to right, and shielding typically stays constant within a period because you're not changing the number of shells. Whereas shielding effect or energy shells, they explain trends sort of within a group, going from top to bottom. And generally, the shielding effect will increase as you go from top to bottom just because you have more shells as you go down the group, right? Because every period adds another shell to it. So again, that explains trends going within a group. So let's just go over this little example here. Here we have sodium and chlorine. And you'll notice that both sodium and chlorine have 1, 2, 3 shells. 1, 2, 3 shells. So they have the same number of shells. So shielding effect most likely won't have much of an effect on a pattern here. But you'll notice there's a difference in terms of the number of protons. This has 11 protons for sodium, and this has 17 protons for chlorine. So this will have a stronger effective nuclear charge because it has the same number of shells as sodium, but you have more protons, more positive force pulling in on those outer electrons. So notice that the shielding is similar between the two because there's only 10 electrons between the nucleus and the outer electrons for chlorine and the nucleus and the outer electrons for sodium, which is why it's that effective nuclear force, that charge is going to have a greater effect here than any shielding because it's relatively constant. And so that's why chlorine is going to be smaller as a radius than sodium, for example. And if we look at, let's say, lithium and sodium, sodium is larger than lithium. Even though sodium has more protons and you'd think would be able to pull the electrons in from the outside more closely to it than, let's say, lithium because it has less protons, there is something different here. Sodium has more shells between the outer electron and the nucleus. So there's that shielding effect happening, and there's a greater distance from the nucleus as well for the outer electron, which is why even though there's more protons for sodium, it's not going to have necessarily a stronger pull on the outer electron just because it's so much farther away and there's that shielding effect happening. And so that explains why sodium is larger. And it also explains why, we'll learn later on, why sodium is more reactive and more metallic. Basically, when I say more reactive, it's more likely to give away its valence electron because it just doesn't have a strong hold on it like lithium would. Lithium has a bit of a stronger hold on it compared to sodium, for example. And so we're going to be able to explain all those trends using the concepts of effective nuclear charge and shielding or distance from the nucleus. And we're going to start off with the atomic radius. But before we do that, let's go ahead and fill in some blanks to make sure we understand the concepts of what a periodic trend is, and also what two main factors explain it. So we have our periodic trends, which are regular patterns, repeating patterns that can be observed in the periodic table. And one example we talked about, the easiest one, is the atomic number and the mass, how they both increase going down a group, and also going across a group. When we say across, we usually mean left to right across a group. And the main trends we're going to study are these trends over here. So we're going to focus on those. And to explain those trends, we're going to focus on using two main factors, the effective nuclear charge, abbreviated ZF, and also the shielding effect. Shielding effect. So the effective nuclear charge, as we mentioned, is a measure of the attractive force between the nucleus and the valence electrons, or the outer electrons. And usually the effective nuclear force goes up. So goes up from left to right across a period. And that's because the number of protons in the nucleus increase and the shell number stays the same within that period. So each electron is going to experience a greater force from the nucleus just because there's more protons in the nucleus as you go from left to right. So for example, there's more protons in fluorine compared to lithium. So that's why the electrons in the valence shell of fluorine will experience a greater pull than the electrons in the valence shell of lithium. And they have the same number of shells, so there's no greater shielding effect between fluorine and lithium. So generally, the effective nuclear charge is used to explain trends going across a period or across a row, period/row. So like this. Okay. And that's because, again, the shielding is constant. Now, shielding, repulsion, and distance, that's the idea that as you go down a group, there's more and more shells. And so the outer electrons, even though there might be more protons in here in the nucleus, don't experience a strong pull just because there's more electrons kind of in between the outer electrons and the nucleus. And those inner electrons will push away the outer electrons even more because they have the same charge and they repel each other. So the inner shell electrons will repel the outer shell, the outer electrons in the atom, and also um, uh, they'll repel them, and then they'll also reduce or protect. I should say protect the outer electrons in an atom from the attractive force of the nucleus. They diminish the attractive force that's there. So if we take a look at that example one more time over here. Or that's the better word to use. I forgot that word for a minute. They shield the outer electrons. Protect was the word I was thinking of, but it's they shield the outer electrons from the from the nucleus, from their pull. And generally, the shielding explains the trends within a group or column. Within a group or column, or you might sometimes say family, but that's generally what explains those trends as we saw earlier. And in the next few videos, we're going to take a look at the various trends that exist. We're going to spot what the trends are and explain those trends using the concepts of effective nuclear charge and shielding as well.